All right, guys. So I'll be talking about maintaining plasticity in deep continual learning. This is work done with Fernando, Parash, Rich, and Rupam. So I'll just start with the main message, so everyone is on track of what's happening. And it's that standard deep learning methods can fail in continual learning problems. And here, by fail, I mean that learning slows down and eventually it goes down to a very low level. And by deep learning, I'm talking about methods that are specialized to work in the train one setting where you just collect a lot of data and train on it. Okay. And we can find better learning algorithms, but we need to look for them and get out of the standard training setting and work more on the continual learning problems. Okay. So first question is, why do we want to do continual learning? Well, the first thing to note is that the standard deep learning methods, they're specialized for this setting we are calling train once, where what you do is collect a lot of data and then train on it once, and then you never train on this again. Like the network, the model is deployed and then you don't do anything else. All the successes of deep learning have been largely in this setting, like from image classification and speech recognition in like the early 2010s. Then we got some good successes in RL, but essentially what we were doing was using replay buffers and target networks to try to avoid non-stationarity as much as possible and just change the problem setting to the one where we can solve it. We have algorithms to solve it. And even now, when we have these very fancy tools like ChatGPT, where you collect the entire internet, if you ask it about anything that has recently happened, it tells you that, oh, my training only goes up until 2021. I don't know anything about it afterwards. So clearly there's still room for continual learning. We still have to be able to learn new things. Okay. But if you use standard deep learning methods, there are problems. The first one is the issue of catastrophic forgetting, which everyone knows about. But this talk is about something different. We're going to focus on this issue of loss of plasticity. This was shown in the early neural networks, but in the psychology literature. So it's not very well known in the machine learning community. There are some very recent papers that talk about failure of warm starting. So warm starting is like pre-training. You train on half of the data set, and then you train on the entire data set. And sometimes what ends up happening is that the performance, if you pre-train, is worse than if you had not pre-trained, which sort of goes against the common view in machine learning. And then there are these couple of recent papers in deep RL about primacy bias and capacity loss that show that there is this loss of the ability to learn in RL. Although all of these papers are interesting, there is no direct demonstration of loss of plasticity in supervised learning. If we have a continuous supervised learning problem, is there a loss of plasticity? That question has not been directly answered, and that's what we'll try to do. But before that, just to make sure we are all on the same page, when I'm saying plasticity, I mean the ability to learn. And when it's loss of plasticity, well, you're losing the ability to learn. You're not being able to learn continually. And then it's hard to say that it's a continual learning system. And maintaining plasticity just means that you're maintaining the ability to learn. Yeah. Also, feel free to ask any clarification questions. I am hoping that I can explain everything in the talk. So yeah, questions are welcome all the time. Okay.
Is it the same as L to warm start? Because you can think of the new type is the.
In some sense, they're similar, but I'm using the term in the continual learning setting that is not exactly continual because the underlying distribution remains the same in the warm starting setting. Yeah. Okay. So the first part of the talk is well, we will try to demonstrate loss of plasticity. We want to make a direct test of continual learning. And one idea is we can use a non-stationary task where things change, or the other idea is to use a sequence of different tasks. And we never tell the learner when the task is changing. And it can be a reinforcement learning problem, but reinforcement learning has its own issues. It causes a lot of confounders. So we're just going to do simple supervised learning. And if you're going to do supervised learning, we can just do classification. And if you're doing classification, maybe we can just use something like ImageNet or MNIST. So let's go to the first problem, the ImageNet data set. So what is it? It's a collection of images, around 1 million images, with 1,000 classes, and each class has at least 700 images. And it's used to learn this labeling from images to classes. We'll use this data set to make a continual learning problem, which we call the continual ImageNet. And the goal here is to seek minimal change from the deep learning practice in the way things are done. So you want to stay as close to the standard setting as possible. So what we have is a training set and a test set. Each class has 600 training examples and 100 test examples. And then we make pairs of classes, which ends up giving us 500 classification tasks. So first, for example, we present the class one and class 2 with 1,200 examples, and then 200 test examples, and then so on. We have 500 tasks. And the performance measure is the percentage correct, which is the accuracy on the test set at the end of training on each task. And these results are averaged over 30 runs, varying, like this pairing in the second run class 1 can be against class 4, and so on and so forth. And the test set is also very okay. So the network we are using, first of all, across the task, the network remains the same, except a small change where the head that's used to identify the class, the output layer, that is reset at the end of each task. We're using a standard neural network with 3 convolution layers, 3 fully connected layers, although this is slightly narrower than the commonly used networks. But that's just because we're only classifying 2 classes at a time. And for each task, we have 1,200 examples. So we use mini batches of size 100. So there are 12 mini batches, and then we do 250 epochs through the data. And weights are initialized using the K-mean distribution only once before the first task. We're using SGD with momentum on the negative log likelihood loss using Halo activations. And these are the final choices, but we did a lot of variations on the initial distribution, activation function, and all this just to find a representative performance. And we wanted to obtain good performance in the first task. So we essentially want to test if we have a network that can learn well on one task, can it learn well on the next task? Can it learn on a task after that? So that is the goal. Okay, so that's what we want to see. So let me explain what this plot is. Here on the x-axis, we have the task number. On the y-axis, we have percentage correct on test set. So after training for 250 epochs, we want to see what is the accuracy on the test set. The green line is the performance of a linear network, where you just directly learn a linear mapping from the pixels to the heads. And the other 2 are performance of backprop on that network for 2 different values of the step size. And if you just predict randomly, the accuracy will be 50%. And the shaded region is the standard error. What we see is that there is a small drop in performance for the larger step size, but for the smaller one, there is maybe a drop, but the difference is not significant. But what if we learn for longer, for more than 10 tasks? So here's what we see. This is the same experiment, but for 2,000 tasks. For brevity, we are using bins of size 50. So the first data point is the average accuracy on the first 50 tasks. The next is on the next 50, and so on and so forth. And again, the y-axis is the accuracy on the test set at the end of training. Okay, so if you remember, the accuracy on the first task was around 89%, but by the end, for the step size that performed very well, it's below 75. It's worse than the linear network. And for the other step size, it's not that much better than a linear network. Again, this data is representative, so the details will change if you change the number of epochs and step sizes and network size. But the same phenomena occurs across different variations of networks and experiment settings. We're just presenting one because here for each line, it took about 24 hours in Compute Canada to finish one experiment. Okay, so what can we conclude from this experiment? Well, we can say that for good hyperparameters, there is loss in performance. There is a loss of plasticity across tasks, and it nears the level of the linear baseline at the end of 2000 tasks for all values of the parameters. And we can even say that there is a catastrophic loss of plasticity in this problem. Okay, now we move on to the next problem, which is MNIST, because it's smaller and you can run faster experiments if you want. And we'll do some more experiments, more deeper dives into things in MNIST. So what's MNIST? It's a collection of 60,000 handwritten digits with 10 classes from 0 to 9. And these are grayscale images with 28 by 28 dimensions. So this is a digit 7. This is an example of an image. We'll use the permuted MNIST task. What is it? Well, you have the same images, but you just permute all the pixels randomly. But obviously, with this problem, we cannot use a convolutional network because we've lost the spatial information. So we will just use feed-forward network, and for them, it doesn't matter if you permute things or not. And now we make a continual MNIST problem out of it. So this will be a sequence of permuted MNIST tasks. And in each task, we'll present 60,000 images in random order. And we don't tell the network when the task has changed. Again, the weights are initialized just once before the first task. And again, we are just reporting. We are using the negative log likelihood loss, and we're measuring accuracy. But there is a slight difference. We're using online accuracy instead of the accuracy on the test set. So there's no notion of a test set. Each image is presented just once, and we're seeing if the network gets that right or wrong. So that's how we're measuring. Okay. So the network, we're using a standard neural network for fully connected layers with 2000 hidden units. Again, this is 1 out of 10 classification. This time, however, we are not reinitializing the heads when the task changes. So the network this time has no idea at all when the task is changing. Again, the weights are initialized using k-mean distribution, but just once before the first task. And these are results with SGD, and this time no momentum. On the cross inter, sorry, this should be the negative log likelihood loss, and on ReLU activations. Okay, so this is the performance. So what it is the accuracy on each example. So what happens is that you're presenting 60,000 examples, the network learns to classify, gets up to like 96, 97% accuracy. And then when the task changes, obviously its performance is going to drop. But then it learns on the next task and on the next task. So it starts to look like an alligator's tail. So we call it an alligator graph. Yeah. One other way to represent this data is through these blue dots. So what are these dots? These dots are the average performance over these 60,000 examples. So this is the average accuracy for these 60,000 examples. So what we see is that this average accuracy is getting better over time. And that's sort of what we would expect from the normal intuition in machine learning, that if you're pre-training on something, that the performance will improve. But again, this is just 10 tasks. What happens in the long run? Now these are superimposed spikes. So the blue line is just the first task, and then the greenish line is the 10th task. So the performance on 10th task is much better than the first. And if you see after the 100th task, the performance is about the same, slightly worse than the 10th task. But after like 800 tasks, there is a significant drop from the peak. So there has been a loss in performance. Okay. So what we're seeing is that the plasticity improves over early tasks, the performance is improving, but then it degrades. So let's look at this longer term plot. So first is the effect of the step size. So if you have a smaller step size, if you have a large step size, the effect is much sharper. Oops. The performance drop is very sharp, and by the end, you are about 90% accurate. And but for smaller step sizes, the drop is smaller, but it is still there, and it's almost linear after the initial phase. Like these lines remain linear for all step sizes. Now, what happens if we change the size of the network? Well, if we have a smaller network, the drop is much faster. So these are just 150 tasks. But for a network of size with, let's say, 10,000 with millions of parameter, hundreds of millions actually, the drop is significantly slower, but there is still a drop. And we'll have, yeah. So there is loss of plasticity for all step sizes, and even for like larger networks, there is a loss of plasticity. It's just slower. Okay. Yeah.
If you ran the network with 10K out to 800 tasks, does it continue to degrade? Or is it
I couldn't run because, well, the network is so big that on Compute Can, I can only run experiments for a week. It almost takes that much. It has like 600 million parameters. Yeah, but I would guess that it would keep dropping. Yeah. Okay, so we're through the first part. We've demonstrated loss of plasticity in two problems. Now we'll try to see what's happening in the networks. Why is there a loss of plasticity? We'll try to figure out if we can understand something. Yeah. So the three different plots will start on my right hand side, so your left, I think. Anyway, this side. So the first thing I'm showing is the percentage of dead units, which is, and what is a dead unit? A dead unit is one whose output is always zero and is no longer useful for learning anything. And what we're seeing is that for different step sizes, there's a different rate for which units are getting dead, but for all of them, the number of dead units is increasing with time, increasing with tasks. So for like this largest step size, almost 30% of the units are dead. The next thing is the weight magnitude. And if this is the average weight for all the weights in the network. And again, the weight magnitude is increasing. Why is this a problem? Well, if the weights are too large, then it's hard to change the relative representation in each unit. So they're becoming too committed and are harder to change. And again, for different step sizes, there's different rate at which the weights increase, but they increase for all of them. And the final thing is the effective rank. So the effective rank in some way is trying to measure the diversity or like the representation capacity of the network. And what we're seeing is that for all step sizes, there is a drop in representation capacity. So they're losing their ability to represent solutions. Let's say the solution space is the representable space is getting smaller. Yeah. Okay. So hopefully, I think these three things do explain partially all of them. Why is there a drop in performance? If the units are dead, well, they're useless. If the weights are too large, it's hard to change things. And again, if the representation is falling effectively, in some sense, we can say the network is getting smaller. Yeah. Now let's try to see existing methods, use some existing methods and see if they can help us in maintaining plasticity. This should be fun. Okay, so what we have, again, this is the performance of backprop for one of the step sizes. And this is the number of dead units. This is the weight magnitudes. This is the effective rank. So the first thing I'm going to test is Atom. Atom has a bunch of, so this was vanilla SGD. Now, if we use Atom, what do you guys think will happen? My guess was that it should help in some way, but yes, but I think it will still surprise you just how bad Atom is. It's like in less than 100 tasks, it's gone. Like the drop is just so much worse. And this was the best performing Atom for different parameters of betas and step size parameters. It was even worse. Let's see in the networks inside Atom, using Atom. So, well, the dead units, there are lots of dead units, almost like 40% of the units are dead. Weight increase is about the same as Atom, and sorry, same as backprop. But the effective rank has just completely collapsed. The networks is like less than 5%. Like it's so much worse. Okay, now let's look at another method. We're looking at dropout now. So this is what dropout looks like. So what is it? Dropout, you hide like, let's say 10% of the units of the network for each pass, and they're randomly chosen. And the idea behind it is that it would decorrelate the units, and that there would be better generalization and things like that. But for whatever reason, what we found is that the more dropout there is, the more fraction of units you hide, the worse the performance is. So the best performing dropout was actually one that had no dropout.
So this is dropout with SGD.
Yes, these are all with SGD. Yeah, sorry, this is Adam, this is with SGD.
Quick question.
Yeah.
Does the when you what was that me? When you measure the death, what units are dead? How do you check that? Is it for all possible inputs there is never any output, or for inputs experienced over some horizon?
Yeah. So obviously, a unit can never be dead, in the sense like there would always be some inputs for which it will be active. What we are looking at here is like for the current task, if you pass in all the images, it's never active. So for the current task, it's dead. And we check it before starting to learn on this task.
So before learning this task, we check if it's dead on all possible inputs for this task.
Okay. Yes. Okay. So for dropout, the results were somewhat surprising. We didn't understand them too well, to be honest. Like the dead units are about the same as backprop. The weight increases about the same as backprop, and the rank remains the same. So this is sort of a mystery still, why dropout is performing worse. It's not clear to us. And yeah.
These dead units also include the turned off units. So they're like 10%.
No.
Ignore it. Oh,
Yeah.
you turn on everything. And
Yeah. Yes. Okay, so but we'll leave that for future work. Someone will figure that out. Okay, the next one is online norm. So this is an online problem, and online norm is an online variant of batch norm. So what you're doing is normalizing before the activation, and you're keeping running averages of running estimates of means and variance to find the normalization. Yeah, and as you can see here, it performs much better in the beginning, but then there is a sharper drop than backprop. So what happens in the network in online norm? Well, there were like no dead units by design, but then the estimates were out of order, and then you start getting a lot of dead units. The weight again increased as we expected, and then the effective rank was very high in the beginning. It even increased, but then there is an even sharper drop with online norm. The next thing is L2. Okay, something that helps finally. So, well, what is L2 doing? So L2 regularization simply shrinks the weight on each update. So the weight magnitudes would stop growing by design. And that's what we see here. The weight magnitudes don't increase. But what about these other things? Dead units and effective rank? Well, there are more dead units in the L2 network than backprop, and the effective rank is also significantly lower. And yeah, so what this suggests is that we can probably still improve things. But these are like the most commonly used methods, like Adam, dropout, normalization, regularization. When only regularization seems to help, everything else just makes it much worse, which is problematic because we just pick these methods from the train one setting and then use it in continual learning problems. And that's not good. We need to fix this. But there's other method called shrink and perturb, which was introduced by these people who worked on warm starting, and it performs pretty well. It almost fully solves the problem. So what is shrink and perturb? Shrink and perturb does L2 regularization, as the name suggests. It shrinks the weights on each update and then adds random noise to them at each update. So again, because the weights are being shrunk, as we would expect, the weight magnitudes don't increase. And the injection of randomness also stops the number of dead units from increasing too much. Only it plateaus at around 10%. And the effective rank is higher because there is more randomness. It's higher than L2, but still worse than backprop.
So the perturb part isn't perturbing anything, or like are they choosing what to perturb?
No, it perturbs all the weights in the network.
Okay.
With some variance. Yeah. Okay. Yeah, so shrink and perturb helps, but it seems like we can still improve because we still have a lot of dead units and the effective rank is still lower than that of backprop. So maybe you can improve this, but I want you to take away this note that this is probably the most surprising result from all of this, is that the injection of randomness was critical for maintaining plasticity. Like L2 regularization on its own did not fix this problem. So we needed this thing called shrink and perturb. Perturbation on top of regularization to help fix. Okay.
Why is it so kind of obvious?
Is it?
No, I also see this.
I would say that because, well, it's not part of the standard toolkit in machine learning. Nobody uses perturbation. So why would we expect it to help? Like this is the only non-standard thing. Everything else that's standard isn't helping. So my guess is someone who's practicing standard deep learning would be surprised to find something outside of the standard toolbox to help. Maybe.
Do you have any, sorry, do you have any intuition about why dropout doesn't work? Because it's also somehow related to memory.
Good point. I don't know. I really have no idea why dropout is worse. Yeah.
Token theory point, but there's this sort of thing that like when you're doing online learning, there's a danger of overfitting to the history of data that you have seen. And sort of there's two standard approaches that you need to do, that you can prove that you need to do, are the regularization, so that's something we talked about. But the other is like perturbation. And people have shown that perturbation in different domains is helps and is sometimes also equivalent. So you can either perturb the hypothesis that you're online generating, or you can perturb the data that you have and train on that. So and many of these kind of similar things, but yeah.
I see. So this aligns with those results pretty much.
Follow the perturb leader, like one of that or
Okay. Nice.
Kind of related to that, I don't know the shrink and perturb algorithm that well, but have you looked at perturb without shrink?
I have, and it doesn't work.
Oh, really? Okay.
Yeah. And the reason, my guess is that, well, the weight magnitudes still keep increasing and the perturbation part, the variance stays fixed. So effectively, let's say your weights have increased like 3 times, but the variance you're adding is still the same. So effectively the variance is getting lower. So it doesn't help. That's my guess. Yeah.
Thanks.
Okay. Yeah. So all of our ideas and algorithms came from this slowly changing regression problem. And this was part of my master's thesis. So some of you probably already have seen this part, but I'll quickly go over it. So what is this? This is a small problem. It's a new idealized regression problem for continual learning. What we have is we make up a target function and an input space. The target function is a network with one hidden layer and random weights that are plus or minus 1. And the activation function is an LTU. There are 21 input bits, so they can be 1 or 0. 1 is always constant. There are 5 IID, so they are randomly sampled. And then there are 15 slowly changing ones. So what are slowly changing one? Well, after every 10,000 steps, we pick one of these and flip it. So what ends up happening is that in some sense, you can think of like the target function stays the same, but you're moving around in the input space slowly because there are only these 5 bits that are regularly changing, others change much more slowly. Yeah, as I said, this results in a slowly changing target function in these 5 rapidly changing bits. Okay. Again, we use the same network, same structure, but the network is smaller, the learning network, so that it cannot exactly represent the target function. So you have to track the changes. Okay. This is just to show that this is a simple problem and we can use it to quickly replicate everything in like 20 minutes. And we can do a lot of experiments. I'm not going to go into details. These are just to show that you can vary everything. Like if you use different activation functions, there is still the same issue in a regression problem where the squared error increases and things like that. You can use all algorithms, again, do more studies, and then you can use Adam in all of these problems and the issues remain the same. I'm not going to go into this. This is just that we can use these simple problem for everything. Okay. Now I'll reiterate the main message we had, which is that standard deep learning methods, they can fail in continual learning problems. And again, by fail, I mean that there is a loss of the ability to learn. And eventually, in many cases, they just cannot learn anything. And by deep learning, I mean the standard methods that are specialized to work in this train one setting. Again, better learning algorithms are not hard to find, but we need to get out of the standard train one setting. We need to be brave. We need to face the non-stationary problem. I know it's hard. There are not even good mathematical frameworks for the problem, I think. They're either too general and too scary, but we need to try to face the problem. It's future, I think. Anyways, okay, so now on to the last part of the talk, where I'll propose a simple algorithm, which is a very simple extension of backprop. And it seems to solve the loss of plasticity in all the problems we've tested. Okay. So the first question I want to ask is like, is the standard backpropagation algorithm continual? Just to define the conventional backprop, I'm saying this has two parts. Initialization is small random weights and gradient descent at each time step. I would argue that it's not, because it does this special computation in the beginning, which is never repeated again, which is initializing weights with small random numbers. And if this was not important, maybe people would not have figured out all these fancy initialization methods like k-mean and everything. So this, I think, is a suggestion that if you want to do continual learning, you want to use this thing continually. So that was the hint, and we want to make this continual. One idea is to reinitialize the network. And there are some recent work, the primacy bias paper, if some of you are aware, they just reinitialize the network once in a while. But the downside of doing that is that you have to store everything you've ever seen. And then when you reset the whole thing, your performance is worse for a while. But what we will do is we'll just reinitialize parts of the network slowly and continually. So we don't need to store everything you've ever seen. And again, it's better to initialize selectively than, for example, using a notion of dead unit utility where you can reinitialize dead units or something like that. This idea of selective reinitialization was proposed by Rupam and Rich in 2012, and they called it Genet and Test. So it builds upon that, but that work was very limited. It didn't combine this idea with gradient descent. It was just random search, and it's not that powerful. And it was limited to this very small case of a network with one hidden layer and one output. And we generalized it to deep networks, even convolutional networks. Okay. So we do some extensions on top of their work. The first one is we generalize to multi-layer networks where fan out is greater than one. So fan out meaning for each hidden unit, how many consumers there are. So they were limited to the case where there was just one consumer to each unit. So yeah. So just, for example, regression problems with one hidden layer. And yeah, and their utility measure was just based on the weight magnitude. So if a unit has large outgoing weights, then it was considered important. We also consider the feature activation for this in our utility measure. And we also consider how fast you can change, how fast a feature can change its representation when computing its utility. And this extra step we do is to reduce the effect of removing the feature. So when a feature is removed, its average contribution is moved to the bias. So this is all very complicated and leads to this very scary looking utility measure, but it seems to work. I'm not going to go into the details of that, but it's just there. but obviously there's more to be done. This is still a local measure of utility. It only looks at the incoming and outgoing weights and activation, but not how this unit is affecting the entire function. So there's more work to be done in how to measure utility. And of course, instead of having random generators, like just reinitializing with the same distribution, we can probably do better. Okay, so this is the algorithm. Let's look at how it does on the permuted MNIST problem. This was the, again, I'll just remind you, this is the online accuracy. This is the task number on the online permuted MNIST task. And if you remember, backprop's performance got worse. Only L2 and shrink and perturb helped. But continual backprop does a bit better than shrink and perturb in this case. But I think the more interesting thing is that it's very robust to its main hyperparameter replacement rate. So for example, replacement rate of 1e minus 4, and this network has 2000 hidden units. So what this means is like this much fraction of units are replaced at each update. So this times 2000 is 0.2. What that means is like we replace 1 unit in each layer after every 5 steps. So, and for this one, this corresponds to one unit reinitialization after every 500 steps. So there is a very slow reinitialization, but it is continual. Okay. Let's look at the network inside continual backprop. The network that's using continual backprop. As you can see, it has a very small fraction of dead units, and this is not surprising. This is sort of by design. The utility function finds out which is a dead unit. It has zero utility and it will be replaced immediately. So there are very small dead units. And again, because you're reinitializing from the same distribution, the growth in the weight magnitudes has stopped. And again, because we are reinitializing, there's a lot of randomness. Continual backprop has a higher effective rank than backprop. So it seems to solve all the problems, all the correlates of loss of plasticity in the MNIST task.
Do you have?
Yes, sorry, go ahead.
Do you have a comparison of the different components? Like, I'd be really interested in randomly replacing a node, not sharing the weights to the bias, or like all, because there's kind of the 3 pieces to the randomly reinitialize and pay attention to which ones you reset, and also save the weights. So do you have any kind of ablation comparing those 3 aspects?
Right. So not of those 3, but I have ablation for different parts of the utility. So the only part that's missing in the ablation, I think, is moving to the bias. But you can look at, like, break the utility measure down into all its components and then look at it. And I'll show the slide at the end, but it performs much worse.
Thanks.
Okay. Okay. Now let's look at continual backprop on ImageNet. So after 5,000 tasks, its performance is better than what it was in the beginning, which was around 89%. And again, this is for 5,000 tasks. L2 regularization and shrink and perturb both help a lot, but only continual backprop seems to do better than what it did in the beginning. Okay, this is for 5,000 tasks. Now the final sort of experiment that we did was an extension to a RL problem, which we call slippery ant. What it is a pi-bullet environment. An agent controls this ant-looking robot, and the robot is rewarded for forward movement. And how we make it non-stationary is by changing the friction between the surface of between the robot and the floor. And we use a continual version of the PPO algorithm. So this is how the performance of standard PPO looks like. It performs very well on the first task, but when the friction changes, it doesn't learn as well. And then after like changing the friction 10 times, its performance is much worse. L2 and shrink and perturb both help a lot. Continual PPO also helps, but even with it, there is a small loss of plasticity. Like there is a bit of a drop in performance. And I think this is due to some interaction with deep RL. Like more work needs to be done simply. Let's look at the behavior of the PPO agent after 100 million steps. After at this point, it's barely able to move forward. The goal is to learn to move forward. But if you look at the continual PPO agent, it's almost running, which is so nice. Okay. Yeah. So again, a PPO shows a similar drop in performance as backprop, but continual PPO is able to maintain plasticity, but not all of it. There is still room for improvement. And this is not as extensive as of a study as the supervised learning problem. So I think this would be good for future work. Okay, now to the main conclusions. What have we done? Well, we provided the first direct demonstration of loss of plasticity in continual learning problem. And I think this is the main contribution of showing that there is a problem that needs to be addressed. And we showed that deep learning methods that are optimized for the train when setting, and many of them just totally fail in continual learning, for especially Adam. That was somewhat surprising. Like, why did it so much worse than everything else? And then we can have simple changes like continual backprop that can make it effective, but we need to go out and look for them. Especially with continual backprop, though, I think the main limitation is this very complicated utility measure. I'm sure there is a better, simpler utility measure that we can find. And yeah, this opens an exciting world for deep networks that can learn continually. We'll have a chat GPT that will be up to date. Instead of having to retrain it every 5 days, it can probably just learn from the data for the last 5 days. Okay, thank you very much. Yeah.
So can you go back to the ImageNet results, the most recent ImageNet results? Not all the way back, you're going way too far back. The one with continual back.
Oh, okay. Where is it? Yeah.
So I'm curious of why L2 regularization doesn't seem to have the same kind of behavior in this problem as compared to permuted in this.
I see.
And like, what properties of this specific like continual problem do you think?
So there are two interacting factors in the problem. One is forward transfer, which is like how similar are the two tasks. So if the tasks are similar and there is no loss in the ability to learn, we would expect the performance to just keep increasing. And then the other aspect, which is of loss of plasticity, which we're seeing, is that the performance is dropping because the networks are no longer able to learn. In the MNIST problem, the pixels are fully permuted, so there is less similarity between tasks.
Yeah.
So that effect of forward transfer is much less significant than in this problem. And I think those two overlapping factors make it hard to study loss of plasticity in this problem because, well, that factor might be dominating.
So I'm just as a follow-up, I'm curious of like some of the other methods you tried on permuted index.
Yeah.
And how they like, it just seems like there's a break in continuity with like how your results or your hypotheses and conclusions generalize beyond just the permuted. That's right. Like there's some question there. Well, we can chat offline about that.
Okay. Yeah, sure. Yeah.
So I can identify two potential reasons for the loss of plasticity. For example, your first algorithm, so the first task, like Adam, gives you a very bad parameter. It's very good for the first task, but it's bad for continual learning. Or the Adam itself is bad at continual learning, but you transfer back to the SGD, it can improve the performance. So what is the underlying cause of the loss of plasticity in certain algorithms?
So the first point you made is that after learning on the first task, what you find is bad for the next task.
Yeah, the parameter itself is bad.
Sorry?
The parameter
Yeah. The
itself is bad. The other reason is the algorithm is bad at continual learning. So the parameter is nothing wrong if you, for example, ChatGPT is learned, let's say, by Adam.
Yeah.
So far, it's very good on the old data sets. The parameter itself is nothing wrong. Then
Yeah.
we can use traditional SGD or your continual
backprop.
backprop to continue learning the new data.
Right.
The other case is the parameter itself is already specialized to the old task, and it can never be recovered, but it works well for the old task.
Right.
Which one is the case?
Right. I think that, I don't know fully, but I think that can be tested quickly.
Yeah, very easily.
Yeah.
By trying Adam with your continual
Yeah.
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 So this is unintentionally related to that question, but if you look at what Adam is trying to do and what it was designed to do, it was to adjust the learning rate to account for the randomness that's in SDD, right? So like if there was no stochasticity, then there would be some optimal learning rate. But since there is some stochasticity, you need to reduce the learning rate to dampen the effect of the noise. And the whole point of Adam was like the theory behind it is to try to find an optimal thing, right? So the assumption behind Adam is that there is some objective function which does not change. And we're getting noisy samples of the gradient, and the noise has some variance, and you need to figure out what that variance is so that you can find optimal step size, right?
Right.
And so if Adam was really good at its job, it would find the biggest step size possible to like perfectly balance, right? But that also happens to like, that almost means that it's not going to do this adaptivity, like, with continual tasks, right? Because if you are trying to adapt to continual tasks, then you don't want to sort of find a perfect step size that just like perfectly cancels out the noise and converges as quickly as possible, because convergence to some fixed objective function is not your goal, right? So I guess it's easy to say that you found something, and then in hindsight, it's easy to say, yeah, it wasn't designed for that. But it almost seems like the design goal of Adam is that short purposes with continual learning. So it should not be surprising, again, in hindsight, that Adam is bad at it.
Yeah.
Which is again like what you were saying about the tension between converting quickly for one task versus continual learning.
Yeah. Those are, yeah. Okay, I guess there are no more questions. Yeah.
I see this trend. I'm trying to understand it. So being a test, obviously, this trend makes sense, but anyways, you pick a suite of simple problems to test the algorithms. You do this grad student descent on it, and you find the best algorithm, and then you test it on the big thing. And maybe it works, then you have a paper, maybe it does not, then I don't know, you do the thing again. Does this make sense to develop algorithms by testing them on smaller problems and then expecting them to work on the bigger ones? Or maybe we should just work on the bigger ones. Like, who cares about all these sensitivity ones or whatever?
Okay, that is a very meta question, but that diverges to like sensitivity. But obviously, if you're doing continual learning, you have to pick a parameter in the beginning. So if your algorithm is very sensitive, that's not going to work, right? But I do like this idea of using small problems because they help us understand exactly what's wrong. Obviously, there are more factors, more issues that arise in bigger problems. And at least in our case, what happened was like we developed all these things on a small problem and they just generalized pretty much perfectly on the ImageNet and MNIST. But yeah, I can see there being issues that sometimes there are more factors in bigger problems. That's just about like how do you want to do your research? Yeah.
So I'm gonna go back to what you were saying. So when you presented this work the first time, my intuition was that Adam would absolutely help. I was very surprised that they did. That's because one part of Adam is to make sure normalize the gradient to make sure that all the ways change about the same. So my initial guess was this happening because the gradients are dying out in such like lower layers. And so they're not changing, and that's why the network is not happening. And if we use RMS proper Adam, all the parameters will change about the same because we won't have this vanishing gradient, and it would help. And it didn't help, but that was very surprising to me.
Yeah, and I guess a follow-up is that it's like when we talk about normalizing the gradients, that we are kind of saying you have some notion of how big a gradient is, right? So you have like a norm on the gradients. With like any vanilla technique, you are just weighting every gradient the same, right? Like the normal computing is like the normal. So it doesn't really matter whether the gradient is applying to the weight at the final layer, or they don't care, right? And sort of the reason that Adam works and is efficient for a large number of layers is because it can't, like it does this sort of weight-wise gradient manipulation, right? So like if you think of a matrix that is multiplying all of the gradients for all of the weights, Adam is only doing like a diagonal matrix, which is why and the diagonal matrix is furthermore like has equal weight on any individual layer of it, which maybe is not the right thing to do, but Adam doesn't really care about that. Right? But maybe that technique that does care is too slow. So Adam sort of a compromise between the perfect technique and something we can actually use for big neural networks. Yeah. So my line of reasoning before was if Adam was perfect at its job, then potentially it would be even worse at continual learning. And because Adam cannot be perfect at its job, then maybe if it happens to help with continual learning, then that's almost like a side effect. But that is not the intended design of that.
Right.
Also, like just to add to that, like a common trend between like the algorithms that fail really badly is that they both have like running averages of things that they need to use to compute the update. And a possibility is that these running averages are just becoming more and more outdated over time and completely unrelated to what really needs to be used. And that's what both Adam and online norm are doing all of that. But are they?
Yeah.
Yeah.
Do you think that? Okay.
So if we tune that parameter beta would be actually.
Yeah, we didn't really tune like Adam. Beta.
We didn't tune Adam on this problem. I tested on another problem that just either delays the drop in performance slightly, so but that doesn't solve it.
It's the same design product.
Yeah.
Even if you tune it really well.
Like a possibility would be that like we're setting like all these running averages for Adam and see if we would do if we would maintain plasticity because we wouldn't have this outdated information. But we wanted to get rid of all that like knowledge about the change in task, so that's what we didn't do any of them.
Yeah, you have.
For continual backpropagation replacing dead weights, could this also help for non-continually changing tasks, but just a normal task that is a large data set?
Yeah, I think so. I have not tested.
We tested it in the project.
Okay, that is a very special case. That's not a big task, you know.
But yeah, the word is really big, then you have to learn a lot. If you have to learn a lot, then you will be lots of possibilities. That's
Yeah. Okay, eat it.
Yeah, so do you think using ReLU is kind of a blessing in disguise here in the sense that like I'm not sure exactly have you tried other activation functions, and I would imagine it's kind of harder to identify the utility, right?
Yeah.
Which is kind of it seems kind of nice that ReLU when certain neurons die, it's kind of I would imagine somewhat easy to identify. It kind of gives you space to reset instead of having to add.
Right. So we tested all these activation functions with all these algorithms on the regression problem, because that's where you can do most extensive experiments, and the same utility measure works everywhere because it has a
So what does that mean in some of these other activations?
Nothing. They don't die.
Kind of,
They saturate. Many of them saturate like 10H or sigmoid.
so then if they saturate, you reset them.
Yeah.
Okay,
So
you
that
still
part
do it.
is sort of measured. Yeah. True.
So based on like the utility function that we use, like the utility would be zero if it's always like if the output is always constant. Doesn't matter if it's not zero of the output. If it's always one, it will still like have zero utility.
Yeah, the utility measure. So this component will become zero. So this is the current activation minus the average activation. So if the activation is always the same, this thing will become zero. So this captures in some sense the informativeness of the activation.
I had a quick question. So for ImageNet, did you also try any standard data augmentation techniques like mix up to see how it compares against L2 regularization?
No, I have not. Maybe that'll help. Thanks. Hey, I guess there are no more questions. Yeah, so thanks everyone. That's great.